Hello. In the last class, we studied the KKT conditions for constraint optimization problems, and we also saw some examples and how to use the KKT first order and second order conditions to get a local minimum. Now, in today's class, we will look at the duality theory. So, this duality theory is very important because in many constraint problems or some constraint problems are difficult to solve directly, and instead one can convert them to an equivalent problem which is easier to solve. And under certain conditions, the original problem and the dual problem will have the same optimal objective function values. So, in today's class, we will look at the duality theory. Now, before we get into the details of duality theory, let us see some example of a two-player zero-sum game. So, let me first explain what this game is. So, this is a game between two players. So, let us call these two players as P and D. So, these are the two players which are involved in the game, and the game setting is like this, that every player has a set of strategies and each player chooses one of the strategies from the respective sets. So, let script X denote the set of strategies for the player P, and script Y denotes the set of strategies for the player D. Now, there is a payoff function associated with this game, and let us call that function as psi xy, where x belongs to the set script X and y belongs to the set script Y. So, each player chooses a strategy from the respective sets of strategies for that player, and the payoff function is defined based on which strategies the two players have chosen. So, for example, let us assume that the set of strategies for the player P is 1 and 2. So, it has two the player has two strategies, and the player D also has two strategies, and we will denote them by 1 and 2. And the payoff function then can be written in the form of a matrix. So, whose entry x comma y denotes the payoff corresponding to the strategies x and y. So, for example, if a player P chooses a strategy 2 and the player D chooses the strategy 1, then the payoff associated with that game is A 2 comma 1. So, the this entry of the matrix A will be the payoff corresponding to 2 1 combination. Now, this game has some rules. So, the first rule is that every player chooses the strategy from the respective sets independently. So, without knowing what the other without knowing the strategy of the other player, the player uses the strategy, and what they do is that they mention these strategies to the referee, and the referee reveals both the strategies independently. The referee reveals both the strategies simultaneously. So, this is the game, that given a payoff function psi, each player chooses one of the strategies and mentions them to the referee, and then the referee reveals both the strategies simultaneously. And then the payoff will decide which player wins or which player loses. So, since there are two players in this zero sum game, every time one player will be the winner and the other will be the loser. So, the game outcome, it depends on the payoff function psi. Now, if let us assume that if psi x y is greater than 0, then P pays an amount psi x y to the player D, and if that quantity is less than 0, then D pays the negative of that quantity to the player P. So, this is the game outcome. So, naturally every player will try to maximize his or her gain. So, P would like to minimize the payoff to the player D, and at the same time D would like to choose the strategy such that the payoff that D receives is a maximum payoff. So, this is an important part of the game, that one player wants to minimize the payoff to the other player, while the other player D, it wishes to receive the maximum payoff from P. So, let us see some example to illustrate this point. So, throughout this discussion, we assume that the minimum and maximum exist. So, if they do not exist, then one has to use the infimum and supremum appropriately, but throughout our discussion we assume that they exist. So, let us see an example game. So, as you see here that the first player P has these two strategies and the second player has the two strategies, and the payoff function is like this, or it is denoted in the form of this matrix. Now, what it means is that if the player P chooses the strategy 1 and the player 2 also chooses the strategy 1, then the payoff is minus 2. So, which means that the player 2 or player D has to pay an amount equivalent to 2 units to the player P. On the other hand, if player P chooses 2 and player D chooses 1, then player P has to pay an amount of 2 units to player D. Okay. So, let us explore the possibilities of different strategies that player P can use, so that it has to pay minimum amount to the player D. So, suppose player P uses the strategy 1, then what happens is that the player D can choose strategy 2 or the max of these two quantities in this row, so that player D's gain is maximized. On the other hand, if player P chooses the strategy 2, then the player 2 will find out what is the maximum of 2 and minus 3, and that maximum is 2. So, player 2 will choose the strategy 1. Okay. So, the player P, what it will try to do is that it will try to find out what is the maximum quantity in the first row and the maximum quantity in the second row. So, max of a 1 comma y over all y's is basically max of a 1 comma 1 and a 1 comma 2, and that is 1, and max of a 2 comma y is the maximum of the quantities in the second row. So, max of a 1 comma y over all y is 1, and max of a 2 comma y over all y's is 2. So, the two quantities are 1 and 2, and since the player P wishes to minimize the payoff to player D, the player P will choose the strategy corresponding to the mean of these two values, and mean of these two is 1, and that one appears somewhere here. So, the player P would like to choose the strategy 1 corresponds to the first row. So, that its payoff to the player D is minimized. So, player P chooses x equal to 1 at or strategy 1 for this particular payoff function. Now, player D will also use this matrix A to decide its strategy, and what player D would like to do is that it would like to maximize the amount that player D receives from player P. So, player D again has two strategies 1 and 2 corresponding to the first two columns, and let us see what the player D does. So, let us look at the player D strategies. Now, obviously, player D wants to maximize its gain or the payoff from this game. So, suppose if player D chooses this strategy, the first strategy, then the player 1 would like to choose minus the first strategy. So, that player 1 or player P receives the payoff of 2 units. So, what player D will try to do is that in the first column it will find out what is the minimum. So, the minimum in the first column is minus 2. What is the minimum in the second column? The minimum in the second column is minus 3. So, if player D chooses the strategy 1, player P will get a payoff of 2 units. On the other hand, if player D chooses the strategy 2, which corresponds to the second column, then player P will receive the amount of 3 units. So, among these two, 2 units is smaller than 3 units. So, player D would like to choose the strategy 1. So, between the two columns, so the minimum in the first column is minus 2 and the minimum in the second column is minus 3, and the maximum among these two is minus 2. So, if player D chooses the strategy 1, then the amount that the player D will have to pay to P is only 2 units. So, it is better for player D to choose the strategy which is y equal to 1. Now, if we look at this strategies used by players P and D, player P uses the min max strategy and the player D uses the max min strategy. So, in some sense these two problems are duals of each other, and in this case the min max strategy used by the player 1 this quantity is greater than or equal to the max min strategy which resulted in the payoff of minus 2. So, the payoff achieved using the min max strategy is always greater than or equal to the payoff achieved by the max min strategy. Now, the game depends on the payoff matrix A. Now, if we change the entries here, the payoff received by each player would be different. Now, in this matrix, suppose we change this minus 3 to the quantity plus 3, and suppose we have a new game which is the game 2. So, only one quantity in the previous matrix is changed from minus 3 to 3 here. The rest of the conditions remain the same. Now, let us look at the player P strategies, which is min max strategy and maximum among the two rows. So, this is 1 and 3 and the minimum among them which is 1. So, player P uses the strategy 1. And if we look at the player 2 strategy, player 2 will try to find out the minimum of -2 and 2, which is -2, and minimum of 1 and 3, which is 1, and the maximum among them. So, that will be obviously 1. So, player P chooses the strategy 1, and if we look at the player D strategy, it will be max min strategy, and as I said earlier, so max of -2 and 1, which is 1. So, player P chooses strategy 1 and player D chooses strategy 2, and they both correspond to this 1. So, that means that in this game the player P which chooses strategy x equal to 1 and player D which chooses strategy y equal to 2, the payoff is 1. That means that player P will have to pay the amount 1 unit to player D. But interestingly, this game is different from the previous one in the sense that the payoff that one player P has to pay and the amount that player D receives, they both are same. So, in other words, so this is different from the game that we saw earlier, where the min max and the max min values were different. So, this is a game where the min max and max min values are same, and it is said that the game is in equilibrium. That means that no player can gain by moving away from these strategies, and this is the situation where min max equal to max min. So, we have these two dual problems, min max and max min, and in the first game we saw that max min was less than or equal to min max, and in this game we saw that min max equal to max min. So, these two problems are the dual problems to each other. The problem solved by the player P, so we are going to call it as a primal problem, and the problem solved by the player D, we are going to call it as a dual problem. So, the primal problem is to minimize some function, and that function is called the primal function, and that primal function is obtained by solving another optimization problem, which is max of psi x y, where y comes from the set of strategies for the player D. If we look at the dual problem is a max min problem. So, the dual problem is to maximize the dual function, which is again another optimization problem to minimize psi x y, where x belongs to x. And we also saw in the zero-sum two-player game that max min is less than or equal to min max, or in other words, the value of the dual function is always less than or equal to the value of the primal function. Now, what is important is that we need to be given this payoff function, which is psi x y, and the strategies for the respective players, which are script x and script y. Now, we will be interested in finding out when the two problems have the same objective function value. So, in that case, it will be beneficial to solve the problem which is easier among the two, so that we do not lose on the objective function values. So, these two problems are dual to each other, and for any x in the set script x and y in the set script y, we know that minimum of psi x y is always less than or equal to psi x y. We assume that this x and y are coming from the respective sets script x and script y. And similarly, this psi x y will be less than or equal to the max of psi x y over all possible y's. So, therefore, we can write that minimum of psi x y is less than or equal to maximum of psi x y because of this previous inequality. And since minimum of this quantity is less than or equal to max of this quantity, then we can write that. So, this is happening for all possible y's. So, even if we take the max of this quantity, that will be less than or equal to the mean of this quantity. So, max over all possible y's, mean of psi x y will be less than or equal to mean of x over max of psi x y. And this is important concept in duality, which is called the weak duality, that max mean value is always less than or equal to min max value for corresponding to this payoff function psi x y. Okay. So, we have seen that this inequality holds for any game. Now, under what conditions this is a equality, and that is what we are going to study now. And for that purpose, we need the definitions of saddle points. So, let x star be from the set script x and y star be from the set script y. The point x star y star is a saddle point for psi x y if this condition holds. So, psi x star y star is less than or equal to psi x y star and greater than or equal to psi x star y for all x in the set script x and y in the set script y. So, this is very important condition, and this is called the saddle point condition. So, as you would see here that if we consider the second part of the condition, psi x star y star is less than or equal to psi x y star. So, if we keep y star fixed, then the function has a minimum at x star y star in the direction or along the coordinate directions x. On the other hand, if we keep x star fixed and vary y, then the function has a maximum at x star y star as far as the y coordinate direction is concerned. So, this is a concept of saddle point where along one direction the function value increases and along the other direction the function value decreases, and this relationship holds for all x in the set script x and y in the set script y. Now, as you can see here that x star is a obtained by minimizing psi x y star or fixing y star and minimizing the payoff function over the set script x. And similarly, y star is obtained by maximizing the payoff function, keeping x star fixed and changing y. Now, it turns out that under the saddle point conditions, the equality holds in this case, and that is called the strong duality. And we will see that theorem now, that the max mean of psi x y is equal to mean max of psi x y if and only if there exists a saddle point x star y star for psi x y. So, under the saddle point conditions, the two problems have the same optimal objective function values. Now, let us look at the proof of this theorem. So, this proof has two parts. And the first part is that we assume that it is a saddle point. We assume that there exists a saddle point x star y star and show that this condition holds. And in the second part, we show that if this holds, then there exists a saddle point x star y star. Note that this x y always come from the set, the respective strategy sets. Now, let us assume that x star y star is a saddle point for the payoff function psi x y. So, by the saddle point condition definition, we have psi x star y less than or equal to psi x star y star, and that is less than or equal to psi x y star for all x in script x and y in script y. And therefore, we can write that max of psi x star y, since this condition holds, it will hold for max of psi x star y also. So, max of psi x star y is less than or equal to psi x star y star, and that will be less than or equal to min of psi x y star over all possible x. Now let us try to get the bounds on these quantities. Now, if you look at the first quantity, so max of psi x star y star is always lower bounded by min max of psi x y, and min of psi x y star is always upper bounded by max min of psi x y. Now, we make use of these two conditions along with this inequality to write that min max of psi x y is less than or equal to psi x star y star less than or equal to max min of psi x y. Remember that we got this condition assuming that there exists a saddle point. That is why this condition holds, and then based on the other two conditions, we were able to write this condition. So, what this condition means is that min max is less than or equal to max min, but we have already seen that for any game and feasible strategies x and y, max min is less than or equal to min max. So, if we combine these two conditions, then for this game we can say that min max psi x y equal to max min psi x y, and that is equal to psi of x star y star. So, this proves the first part of the theorem. Now, the second part, we assume that the equality holds, and then we want to prove that x star y star is a saddle point. So, which means that it should satisfy the saddle point conditions. So, if we look at psi x star y star can be written as max of psi x star y over all possible y, and that is same as min of psi x y star over x. And therefore, so we can say that psi x star y star, which is nothing but max of psi x star y, and max of psi x star y will always be greater than or equal to psi x star y, because we have already obtained the maximum of psi x star y. So, naturally for any feasible y, psi x star y will be less than or equal to psi x star y. And similarly, since this is equal to min of psi x y star, that will be less than or equal to psi x y star. So, min of psi x y star is less than or equal to psi x y star, and if we consider this, that psi x star y less than or equal to psi x star y star, which is less than or equal to psi x y star, then we clearly say that x star y star is a saddle point for x y. So, this shows that if and only if there exists a saddle point, then min max is equal to max min. So, this condition is called the strong duality condition, that max min equal to min max. So, which means that in the zero-sum game that we saw earlier, under this strong duality condition, the game is said to be in equilibrium. So, that means that no player has any advantage of changing the strategy and getting a better payoff. Now, to define the notion of duality for optimization problem, we need to define a payoff function. So, let us consider a optimization problem, which we will call it as a nonlinear programming problem. Minimize f(x) subject to the conditions that hx less than or equal to 0 and eix equal to 0. There are m equality constraints and l inequality constraints. Now, the question is that can we define a game with some payoff function psi, so that the solution to NLP is a solution to the primal problem min max psi xy. So, in other words, we are interested in writing this as a min max problem by defining appropriate payoff function psi xy. Now, once we write this as a function, the primal problem min max psi xy, then we can possibly write the corresponding dual problem as max min psi xy, and that dual problem may be sometimes easier to solve than the original problem. And if that is the case, and if the solutions to the primal and the dual problems are same, then that dual problem is much, and if the dual problem is much easier to solve, then it will be beneficial to solve the dual problem rather than the primal problem. And at the same time, we do not get the objective function value which is inferior than the actual optimal objective function value, if both the problems have the same solution. So, one question is that can we define a payoff function so that we can write this problem as a min max problem, and what is meant by the strong duality in terms of the functions f, h and ez, or in other words, how do we get the saddle point condition in terms of the function f, h and es, or in terms of the payoff function, and that is what we are going to study now. Now, let us consider a problem minimize f(x) subject to hx less than or equal to 0 and x belongs to x. Now, for convenience, we have not included the equality constraints here, but they can be included very easily. Now, let us define a payoff function as a Lagrangian function. So, in this case, the Lagrangian is f of x plus sigma lambda j h j x, where x is from the set x and lambda j greater than or equal to 0. So, in our discussion, this Lagrangian function will act as a payoff function for this problem. Now, the variable x associated with this problem is called the primal variable, and the variable lambda, which is a Lagrangian multiplier corresponding to the constraints, that is called the dual variable. And if you look at the set x, so that set x can be treated as a set of strategies for the first player or the primal problem, and so this x set of strategies is nothing but this set x, and the set of strategies for the second player or the dual problem is the set of all lambdas in L dimensional space, because there are L inequality constraints. So, set of all lambdas in L dimensional space such that all lambdas are non-negative for every j. So, So, the idea is that we define the min max function for this problem or a min max function problem which is equivalent to this problem, and then get a max min problem which is in a dual to the min max problem. So, naturally that dual problem will be a dual to this problem also. So, we define a min max problem which is equivalent to the primal problem P, and then the corresponding max min problem will be called the dual problem D, and we will be interested in finding out the conditions under which the optimal objective functions are of the two problems P and D are equal, and whether the dual problem is easier to solve than the primal problem. Now, one assumption that we make here is that minimum and maximum exist for all the problems which are going to be defined, and if they are not, if the minimum and maximum do not exist, then appropriately one can replace minimum by infimum and maximum by supremum if they do not exist. Okay. So, to avoid the notational clutter, we will keep using min max and one can use infimum and supremum appropriately. Now, the primal function, as we saw earlier, that the primal problem is min max of the payoff function psi x y. So, the primal function is max of the payoff function. So, in this case the primal function is max of L x lambda, where L is a Lagrangian and lambdas are non-negative, and that is nothing but max of f x plus sigma lambda z j x, and if h j x happen to be less than or equal to 0, then this quantity it will always be less than or equal to 0, and therefore, the maximum of this objective function will occur at f x if h j x is less than or equal to 0 and will be equal to plus infinity otherwise. So, truly one should write this as supremum, because under the conditions that h j x greater than 0, this is the maximum does not exist, but as I said earlier, we will continue to use this notation and one can choose to write supremum or infimum appropriately. So, if we look at this primal objective function value, that is nothing but maximum f x if this condition holds, and therefore, we have primal problem which is min max problem. So, minimize with respect to x and maximize L x lambda with respect to lambda. So, this quantity is the primal objective function value that we saw earlier, and we want to minimize this. So, we can rewrite this problem as minimize f x subject to h j x less than or equal to 0 and x belongs to x by ignoring the possibility that h j x greater than 0. So, if you are always interested in those parts of the feasible region where x belongs to the set x and h j x less than or equal to 0, then we can ignore this second possibility of the primal function, and then we can write the problem as minimize f x subject to h j x less than or equal to 0. So, this is our primal problem. So, the min max problem, by defining the by defining the payoff function as a Lagrangian function, the min max of Lagrangian is over these feasibility conditions is same as our original constraint optimization problem. Now, let us look at the dual problem. So, for that purpose, let us define the dual function. So, let us take lambdas to be greater than or equal to 0. So, the dual function is, let us define it as theta lambda, and theta lambda, the dual function is a max min a dual problem is a max min problem. So, the dual function is minimum of the payoff function over the variable x. So, minimum of L x lambda, L this is the Lagrangian function over the set X, where lambda is non-negative. And if you expand it further, it will be minimize f x plus sigma lambda j h x. So, this is going to be our dual function, and the dual problem is to maximize over lambda the minimum of this function over x. So, typically what would happen is that when we minimize this with respect to x, we can write at the minimum x or the minimum value of x in terms of lambdas, and write this as a function of lambda, and then we maximize that function with respect to the condition that lambda greater than or equal to 0. So, this is our dual problem, which is a max-min problem. Now, let us consider a simple problem where we want to minimize x square subject to the constraint that x greater than or equal to 1. Now, as you can see here that this function goes to infinity and has a minimum value which occurs at x star equal to 1, and the optimal objective function value is 1 square, which is nothing but 1. So, the optimal primal objective function value is 1, and that occurs at x star equal to 1. Now, let us write down the Lagrangian of this problem. So, the objective function x square plus lambda into 1 minus x by rewriting the constraint as h x less than or equal to 0. Now, let us see what the dual function is. So, the dual function is to minimize L x lambda over x. So, minimize x square plus lambda into 1 minus x, this I should not be here in this case. So, at the minimum we have x star equal to lambda by 2, and therefore, it is easy to see this because this is an unconstrained problem, because our set x is nothing but R. So, minimize x over R, x square plus lambda into 1 minus x, and if we differentiate it with respect to x, so that is 2x minus lambda equal to 0 gives x star equal to lambda by 2, and therefore, for lambda greater than or equal to 0, theta lambda, the dual objective function value, can be written as minus lambda square by 4 plus lambda, and this is obtained by substituting this value of x star in this objective function. Again, I note that this I is not there. So, therefore, the dual problem is maximize lambda or maximize minus lambda square by 4 plus lambda subject to the constraint that lambda greater than or equal to 0. So, this is going to be the dual problem. As you saw that we first considered the Lagrangian and then eliminated the primal variable from this objective function by taking the minimum, and then we substituted that x star in the objective function and got value of lambda, got the function in terms of lambda, and that objective function needs to be maximized with respect to the condition that lambda greater than or equal to 0. Now, suppose we differentiate this and equate it to 0. So, what we get is lambda star to be 2, and that quantity is greater than 0. So, clearly that is a feasible point, and at lambda star equal to 2, the objective function will be minus 1 plus 2, which is plus 1. So, lambda star is equal to 2 and theta lambda star will be 1, and you will see that the optimal primal objective function value is same as the optimal dual objective function value. So, by converting this problem to the dual problem and finding the optimal dual value, we saw that we got the same optimal objective function value as we would have got in the original case of solving the primal problem. Now, let us see the geometric interpretation of this duality. Now, for convenience, let us assume that there exists only one inequality constant, which is of the type h(x) less than or equal to 0. So, we want to minimize this objective function f(x) subject to the constraint that h(x) less than or equal to 0 and x belongs to the set x. Now, let us define the set G to be the set of all yz's such that y is equal to hx and z is equal to fx for some x belongs to the set x. So, we have the problem minimize fx subject to hx less than or equal to 0 and x belongs to x. Now, suppose we have some set x and we have defined a new space. Let us call that space as a y z space. Note that we have said that y is equal to hx and z equal to y for every x in the set x. So, this set will get transformed to some set G. So, this set is transformed to the set G and so the set G is going to be this set. So, note that what we did was that consider every point here in this set x and transformed it to this yz space and constructed the image of this x in the yz space. For example, a point here will get transformed to some point here. So, corresponding to this feasible x, we take the value of x and then find out what is hx and what is zx. So, hx and zx denote the coordinates of this point in the yz space, and if we collect all such points corresponding to every point in x, we get a set G. Okay. Now, so we have denoted the set G which is obtained from every x in x and by using y equal to hx and z equal to fx. So, let us denote the minimum of the objective of the problem in the yz space as y star z star. So, this is our feasible region, the set G, that is our feasible region as far as x is concerned, but remember that we also have to satisfy hx less than or equal to 0, or in other words y less than or equal to 0. So, that means the actual feasible region for the original problem is because y has to be less than or equal to 0. So, this is going to be the actual feasible region for the original problem. The set G denotes just the image of the set x and not really the actual feasible region, because we had ignored hx less than or equal to 0 there, but here we consider hx less than or equal to 0 also, and this forms our feasible region. Now, we want to find out the minimum of f of x in the feasible region. And you may note that we have defined z to be f x. So, we want to find out what is the minimum value of z with respect to this feasible region, and turns out that this point, which is y star z star, is our minimum point. So, in this space we are interested in finding out this finding out a solution which is y star z star. Now, let us look at the dual objective function. So, for lambda which is non-negative, let us define the dual objective function to be theta lambda, which is equal to mean of the Lagrangian, and the Lagrangian function in this case is f x plus lambda h x, where lambda is a Lagrangian multiplier corresponding to this inequality constraint. So, what we want to do is that if we are given lambda which is non-negative, then theta lambda will find out the minimum of f x plus lambda h x, or in other words theta lambda minimizes in the y z space, it minimizes z plus lambda y over g in the y z space over that part of g where h x is less than or equal to 0. So, if you look at this z plus lambda y is the equation of a line in the y z space with z plus lambda y equal to constant is a equation of a line in the y z space where minus lambda is the slope of the line. So, if we are given some lambda, let us look at this figure. So, we are interested in this part. So, z plus lambda y equal to 0 equal to constant is a equation of a line with slope minus lambda, and lambda is greater than or equal to 0. So, minus lambda will be less than or equal to 0. So, we could have a line so this is the equation of a line z plus lambda y is equal to constant, where lambda is greater than or equal to 0. Now, when we want to minimize z plus lambda y, we want to find out that z plus lambda y which gives us the least value with respect to the feasible region. So, with respect to this feasible region, we will get a quantity which is supporting this set, the shaded region here, and the optimal objective function value is the value z that we get corresponding to the line's intercept on the z axis. Now, among all those possible lambdas, we want to find out that lambda which gives us this optimal objective function value, and how to do that we will see that in the next class. Thank you.